Leetcode 39 combination sum. It's a very important problem. It introduces the idea or the topic of combinations as well as backtracking. So backtracking is a strategy to solve certain types of problems, and that particular problem classifies to that group. Yeah, so we will use backtracking, already saying it at the very beginning. And don't worry, I've used right now a couple hard words, but we will explain everything in great detail. So if you just have fundamentals, you understand how to use loops, how to use functions and recursive functions in Python, you should be able to follow. And it's a medium problem, so it's not very easy, but it's also not very hard. Yeah. Here already in the beginning, they are hinting at everything that it's a combination problem. You don't have to guess. You should be able to read from here and understand what kind of algorithms might come into play, what kind of solving strategies, and so on. So we will talk about it in a greater detail, but let's start with description. Given an array of distinct integers called candidates and a target integer called target. Yeah, so we have two inputs in this time. Usually there is one, sometimes there are two, and very rarely they have like three different inputs, but that's a rare case for Leetcode. So in this case, we have a single number, target integer called target, and a list or an array, like a linear structure of elements. In this case, those are all integers, numbers called candidates. And there is another constraint, even that they are distinct. Yeah, so you don't have to worry. Sometimes we would have to, for example, convert the array or list, as they are called in Python, to set in order to deduplicate. But in this case, it's already given to us, so we can assume that all the numbers are unique here. And what should we do with those both inputs? Return a list of all unique combinations of candidates. Yeah, and of course, combinations already point at uniqueness, but we will talk about it in a second. And our task is to create a list of possible combinations. Yeah, so we can choose numbers from those candidates and combine them in such a way that the chosen numbers sum to target. And so we will have to pick special numbers from this first input so that when we sum them up, we will have, or when we sum them, we will have, we will end up with target. You may return the combinations in any order. Yeah, and that's important thing. They are even saying it explicitly here, but usually when we talk about combinations, the order doesn't matter. The same number may be chosen from candidates an unlimited number of times, and that's also an important thing. So we can repeat. If we have a number in candidates, for example, 1, and we want to have a sum, let's say, of 5. Yeah, then we can choose this one 5 times, and that's already one valid answer. Two combinations are unique if the frequency of at least one of the chosen number is different. Yeah, the frequency meaning how many times they will appear. The frequency of an element x is the number of times it occurs in the array. Yeah, so we can have them in any order, but we shouldn't duplicate from our side. But we can have, for example, I gave this example with 1s and 5s. You can, for example, use 1s if you had candidates where there was 1 inside and you wanted to have target of 5. Yeah, then first option that you have is to have 1, 1, 1, 1, 1, yeah, 5 times. But for example, you could also have 2 in these candidates, and in this case, you could reuse the 1, yeah, and that would be counted as something different if you give another result as 1, 2, and 2. Yeah, so that would be the next possible option in this case. And the last thing, the test cases are generated such that the number of unique combinations that sum up to target is less than 150 combinations for the given input. And of course, with generating combinations, we will usually have at least like a square time complexity. So it will take some computation from the CPU, and it's not that easy to generate combinations. There is like no log n or n log n answer for that. That's why they are choosing very small number here, yeah, to not burn their own CPUs. And the next thing are examples. And the first example has the following candidates: 2, 3, 6, and 7, and the target is 7. Yeah, and we can sum the numbers to have 7 in the following way: 2 and 2 gives 4, and then if you add 3 to that, you have also 7. 4 plus 3 is 7, and 7, of course, itself is also 7. Is also equal to itself. And here's some explanation. 2 and 3 are candidates, and 2 plus 2 plus 3 is 7. Note that 2 can be used multiple times. Yeah, have already discussed it here. And 7 is a candidate, and 7 is equal to 7. There are the only two combinations which are possible. In the second example, we have following candidates: 2, 3, and 5, and the target is 8. Yeah, so the first option is to have 2 4 times, and 2 times 4 is 8. The second option is to have 3 and 3 to have 6 plus 2 gives also 8, and 3 plus 5 gives 8. And the third example, we have that's also possible candidates 2 and the target is 1. Yeah, so it could be such a situation where we have no valid answer, or for example that we have candidates, like that the list of candidates is long and some candidates themselves are bigger than the target, which we should use this information when we will be writing our code to not end up trying to figure out possible results for numbers which are already bigger than the target. So this is something to keep in mind. And that's it. So now let's try to think about all the possible ways in which we can solve this problem. Combination sum. And the task is this is our task. List of all unique combinations of candidates where the chosen numbers sum to target. Combinations and candidates are input as well as target. So first things first, let's start with some theory. Generally, when we talk about combinations, we also talk about permutations or about difference between those two. So what are permutations versus combinations? And basically for permutations, order matters. And for combinations, order doesn't matter. Which makes the combinations much easier to work with, especially in code. Well, here order doesn't matter, and here order matters. Maybe let's draw some arrows to not confuse anyone. And let's create an example. Let's say we have 3 people, A, B, and C, and we want to choose 2 out of them. If the order matters, then how many options we have? AD and BA, yeah, BC and CB, yeah, and CA and AC. Those are considered separate. So we have six options because order matters. But if the order doesn't matter, then we only have 3 options. So those would be the permutations and those would be the combinations. And there are some mathematical formulas for that. So permutation of n and r, where n is the total number of items, or in this case people in a group, that would be our n, and r is the number that we are choosing. So the number of things that we are choosing from this collection. And in such a situation, the mathematical formula is as follows. N factorial divided by n minus r factorial. And easy way to remember this is that n is the bigger number, so the complete collection or the group, and r is the smaller number, the one that we are choosing. And for combinations, as we mentioned, the combinations are smaller, and in fact they are the subsets of the permutation. What we will get? We have exactly the same thing, but also divided by r factorial. So this can be also written as permutation divided by r factorial. And that is something that in case of this problem, you already have it given from the title, even not even the description, but the title itself, that is a combination. But sometimes it won't be that clear. You will have to guess it from the problem description if they're talking about the permutations or combinations, and it matters. The permutations are much harder, and while we'll be writing down the code, I will come back to it and will tell you exactly where, in which places it matters that we are dealing with combinations instead of permutations. But just one last thing, if, for example, r is equal to n, so in this case we had 3, the complete group had 3 items, and we were choosing 2 out of it. So we can even write it down here. First, let's plug those 2 numbers, and then I will come back to the situation when r is equal to n. What happens there? So in this situation, we have 3 factorial divided by 3 minus 2 factorial, which is 1 factorial. So 3 factorial is 3 times 2 times 1, which is 6. So it's 6 divided by 1, which is 6. And that's the thing that we had here. And for combinations, we of course have the same thing, just also divided by 2 factorial. So 2 factorial is 2, and 6 divided by 2 is, of course, 3. But what would happen if r was equal to 3, as I started to explain a minute ago? then we would have 3 factorial divided by 3 minus 3 factorial, which is 0 factorial, which is not 0, it's 1. Yeah, and that would be exactly, in this case, it would be the same. It would be 6, but for combinations, here we will have 3 minus 3, which would give a factorial of 0. And here, instead of factorial of 2, we have factorial of 3. Yeah, so 3 factorial we could cancel out with 3, and we would have 1 divided by 1, which would be one possible combination, yeah, which fits to what I was trying to explain in the beginning, that order doesn't matter for combinations. Yeah? So of course, if you try to choose all the possible people, then you have just one such option. So that's it. The next thing that we should understand, at least generally, is what is backtracking. Let me write some pseudocode, which is general solution to any backtracking problem. And generally, there will be a function which we'll use for backtracking. In this case, we will call it just backtrack. And this pseudocode can be reused almost with no changes or very subtle changes in any backtracking problem. Yeah, so we will jump directly from pseudocode, which is like a general solution to any backtracking problem, to our concrete solution for this particular combination sum task. Right? And we are using some partial result, which can mean anything depending on the problem. And we will have concrete example for this problem in a second. And there is a check at the beginning of the function, which is recursive, where you check, we can even write it down like this, is partial result complete. Yeah, you generally repeat it multiple times up until the partial result meets certain criteria. And if it's complete, then you return. Otherwise, you explore all possible options. So we have you iterate through choices in possible choices. And those possible choices also depend usually on the partial result. Yeah, and if choice is valid, you have some kind of condition, then you can add the choice to partial result. Then you backtrack using that partial result updated, and after that you remove the choice from partial result. Yeah, and that's it. And this kind of approach is used in every backtracking problem. Let's put it here. And now we will try to use it in our problem. Let's call partial result here we will call it path. Yeah, because we will be trying to, and maybe I'll write it down already. We'll be trying to gather as many integers from candidates as possible. So we will have, of course, our inputs candidates and target. Yes, and path will be complete when it sums to target. Yeah, so when sum of path equals target, that will be our termination condition, then return let's just use normal if. And if this is the case, that means that we can return, or maybe first let's add it to some result at parent path. So those are the inputs. And let's also create an output. Let's call it result. The inputs and the output here. And we can move it a little bit to the left to not waste any space. Here we will be looping, loop I from start. So there will be a new variable that will create till end of candidates. And candidate will be equal to candidates on the index I. And in this loop, we will be doing exactly this. So, but first also we check if it's valid. So if candidate is greater than target, then return. Let's move it. And otherwise, we'll add the candidate to the path that we have, or the partial result, if you prefer. So then we'll backtrack using the path and choosing I and path. And in the end, we'll remove the candidate from path. So that's more or less the pseudocode or the line of thought to solve this problem. And we can try it using some concrete example. Here the examples are pretty big, so to generate all the combinations for that, it will take some time. So maybe let's try with some smaller example. Let's say we have candidates equal to 2 and 3 and target equal to 5. And what will happen? Inside this loop, the first candidate that we'll try will be 2. And we'll check, of course, that it's not greater than the target, and we'll add it to the path. And path, we can store it here. We'll first, and also result, we can store as well to see how it grows. So at the beginning, it will be empty. And once we have a candidate, then we will add it to the path. So we do it like this. And then we backtrack and start again from the same I, get another 2. So the first candidates on the position 0 is 2 again. Since we backtrack, we add it to the path. And again, the same thing 3 times up until we will see that it's no longer possible. It's and we can also check it here. By the way, we can even write it down. If the sum is greater than target, then just return. And that would be the first option that we tried. The next one would be the same path when we start the next backtrack, when we would loop and increment I. The next candidate would be 3, and we could add it to this path. Yeah, and then we will check here that is possible path, and we would add it to our result. And the next one, we would start from 3 itself and also explore all the options. So first it will be just 3, then we would add the next 3, and this is everything here. It would terminate, and that's it. So we would, in total, for this, using that algorithm, construct 3 paths, and 2 of them would terminate here, and 1 would be added to the result. That's it. Let's try now to use it in Python. Let's create our variables, of course, results, and in the end we'll return results. We can also sort candidates, since it's not guaranteed that they will be sorted, but it will help us here to terminate whenever we reach candidates which are no longer valid. And the heart of the solution will be, of course, our backtrack function, where we have to provide our path, our starting index. Yeah. So each time we will loop from start till the end of candidates. We can even mark it that this is a variable. This is a variable as well. Sorry. I and this. Yeah, so we need the start, and each time we will be updating whenever we call the backtrack again. And we will also be updating target. Yeah, so here I haven't written it down, but we will use it here as well. So target will get smaller and smaller as we add new numbers, but because we have already this name in our, let's say, global scope, global for this function, and the next function that I am defining is local to this one, or it's within this bigger function, and then we should use another name to not get any conflict, so we can code maybe remaining target like this. And here, of course, is the sum. If the sum of path is equal to 0, or in other words, if remaining target is equal 0, then we can add a copy of our path to the results. If remaining target is less than 0, then there are no possible options for us left, and otherwise we will create a loop for I in range start till plan of candidates. Yeah, and our choice or our candidates here will be candidates on index I. Yeah, and if this candidate is greater than remaining target, then we can return, and otherwise we add the candidate to the path and recall backtrack again. And the start will be I. Why I and not I plus 1? Because we want to reuse the same number multiple times. Yeah? And remaining target will be remaining target minus candidate that we have used. Path stays the same. And in the end, we remove the path from, or the last number from the path, or the last candidate from the path. We just use path pop. And that's it for the whole backtracking story. Now we have to call it. The first starting index is of course 0. The first remaining target is the full target, and the first path is empty list. So let's run and see how it goes. And this after. And I of course have some spelling error. I thought that I copied it, but maybe not. Wrong answer, so let's think. Output empty. Let's see. Here. Instead of appending candidate, I'm appending the whole path again. And here we forgot to return. Take a look again. Results. Looks good. Here looks good as well. So let's see. Okay. This time it worked. And let's see on all the cases. With 87% when it comes to our runtime and 87% when it comes to memory. So what is the time complexity of this algorithm? It's n times t, when t is the target, yeah? Because here we have a loop, which will go n times, but we also decrease it each time. But the number of decreases and the number of times we call this depends on the target. If the target is small, let's say 1 or 0, then you would not have any calls. But if it's big, then it will grow linearly to how big this target is. Yeah? So it's n times t, and we will have some additional space that we are using, mainly the results. We store the results, yeah. So there will be paths, and each path can be also big depending on the target itself, yeah. So the size of the path depends on t. So it will be OT on in the case of space complexity.